Hi everyone, welcome to Pharmaball. I believe that this series of tutorials have helped me to understand the pharmacokinetics in a much better way. This is the sixth part of the tutorial. You can check my other classes on pharmacokinetics for a better understanding. Let's start. There are a lot to know in the world of pharmacokinetics. So we have talked about the intravenous bolus dose and the change in pharmacokinetics. Now try to understand what will result if you give a constant intravenous infusion. Before that, let us follow some assumptions for this session. The first one is that the drug we are considering undergoes no metabolism. The drug exhibits the characteristics of a one-compartment model, and the elimination of the drug follows a first-order process and a passive diffuser. The basic idea of infusion is to reach the steady-state plasma concentration. So in this graph, the concentration is plotted in the y-axis and the time in the x-axis. So if we start at time 0, the rate of infusion, and then after that, with due span of time, the concentration rises and gradually reaches the steady-state plasma concentration. So if you want to calculate to how exactly the rate of infusion need to be figured out, we have to follow this formula, that is rate of infusion equal to steady-state plasma concentration into the clearance of the drug. So now let us try to understand what exactly this graph is. So there are three time points. One is A, one is B, one is C. So at time point A, the elimination is very slow because the drug we have given the drug at the very first time. It is still in the venous circulation. So in that case, the plasma concentration of the drug will rise sharply. You can see there is a sharp rise in the plasma concentration. So and at point B, the elimination starts and hence the rate of increase of plasma concentration slows down. So after that, in the part B, there is a gradual increase in the plasma concentration. So and at point C, the time comes when the rate of elimination of the drug is equivalent to the rate of infusion. So there is no further change in the plasma concentration. So at this stage, we can say that it has reached the steady state plasma concentration. So how much time is required to reach the steady state plasma concentration? For example, let's take a drug with a half-life of 3.4 hours, and we have marked here in the time in the x-axis, that is like first half-life, second half-life, and third half-life. In the first half-life, it reaches the 50% of the steady state plasma concentration. Here we have 4 milligram per ml, and there we have 2 milligram per liter. In the second half-life, it reaches the 3/4 of the steady-state plasma concentration, and in the third half-life, it reaches the 7/8 of the steady-state plasma concentration. So we can presume that at 4 or 5 half-life, it will reach the steady-state plasma concentration. So that is the amount of time that will be required to reach the CSS. So what you can see here is that although we are giving an infusion, it takes a long time to reach the steady state plasma concentration. It takes like around 16-17 hours to reach the steady state plasma concentration. So the next question is that whether there's other way that helps to reduce this time frame. Yes, we can go with a thing called loading dose. So if we give a loading dose at the very first instant or within a few hours of starting with IV infusion, it will help to reach the steady state plasma concentration quite quickly. So in this case, we can see that the steady state plasma concentration has reached within 6 hours. Now just try to just concentrate here. So this is the yellow thing that where we have given the loading dose. So this amount of dose plus this amount of dose, the one that we are given IV infusion, so it will together helps to reach the steady state plasma concentration at the given time frame. So if you have the confusion of what is a loading dose, it's a loading dose used to achieve effective blood levels of drug rapidly without having to wait for the drug to accumulate. That is to reach the steady state plasma concentration. For IV dose, you can just calculate the loading dose. It is equivalent to target concentration into the volume distribution. Whereas for oral dose, we have to divide it the calculation with the bioavailability. However, you just have to think about that there is a factor called Saul factor which also need to be considered while calculating the loading dose. Next, let us discuss about the effect of loading dose plus IV infusion in a two-compartment model. We have two input, one is through loading dose and another is the through rate of infusion. and ultimately both moves into the volume 1, that is the first compartment, and after that it may move to the volume 2, the second compartment, back to the volume 1 again, and again it may be excreted outside from the body. However, to calculate the loading dose in this regard, we have to means we may have the uh, question in our mind that what exactly the target volume distribution will need to be there, whether it depends on the volume 1 or it should depends on the total volume. It depends on the target, that is, and also on the type of drug that we are using in this case. For example, the dose will initially find itself constrained within just volume 1, and therefore the initial concentration will be much higher than the target. The loading dose will eventually redistribute throughout the complete volume, and the drug concentration will further decline. Whether the initially high levels are a real problem depends how quickly the loading dose disperses and the potential of the drug to cause toxicity over a period to re-equilibration. For example, for some drugs like lignocaine, the problem is perfectly real, and the loading dose calculated using the complete volume. So if you take the complete volume, for example, for lignocaine in case of anesthesia, the dose will be too high and it will cause loss of toxicity. So in that case, the lignocaine, the loading dose should be calculated based on the volume 1 and not the whole volume. So some of the important factors that need to be considered while giving a loading dose is that how fast it moves to the second compartment. For example, here in this case, you can see that it moves to the second compartment, and ultimately, even after you give the loading dose plus this rate of while infusion, it did not reach the steady state plasma concentration. So at some point of time, like 1 hour or 2 hours, for a period of that 2-3 hours, it did not reach the steady state plasma concentration, and so it is a below therapeutic uh, dose. And that's why it is very important to understand how the drug behave in the body, how effectively it moves to the peripheral or the second compartment. The other things that need to be considered is the therapeutic window, the half-life of the drug, as well as the benefit versus risk. Therapeutic window, because the thing is that it should not uh, cause toxicity. The moment you give the loading dose, it should not be there in the first compartment and it causes toxicity. So that's why the therapeutic window of the drug need to be understand before giving this loading dose. Half-life of the drugs, because any drug with a long half-life and consequently slow accumulation occurs, so in therefore particularly likely to require supplementation with a loading dose. But if your drug has a very short half-life which accumulated rapidly, so loading dose in this case may not be required. So in that case, we have to know about the half-life. So that's what are the things, that is important points that need to be considered while taking judgment whether to give a loading dose or not. So I found this graph very important. It's interesting basically. So that's why I put it. We have already discussed it. In the very first figures, it shows that the plasma concentration. And this is the loading dose. This is the maintenance dose. This plasma concentration decreased after the loading dose, but it to be remembered that you were injecting drug uh, concurrently. So at time 1 or 2 hours, the amount of drug in the body is from the loading dose, okay, and also from the rate of infusion directly into your bloodstream. And thereafter, with the infusion, the drug reaches the steady state plasma concentration. So basically, we have to add the loading dose as well as the IV this infusion rate together and try to see the concentration at that time point. So I have added this, that people actually, my colleagues used to forget about that we have to add both the concentration, both the drugs, because we are giving simultaneously about both the drugs, loading dose and the infusion rate. So we have to add together and to see whether what is the concentration. Practically, we will just draw the blood and we will see the concentration. But if we plot in this in the graph, we generally miss to think about it, that we have to add both the concentration, both the drugs together. Just want to add one more slide, that there is another way to reach the steady state plasma concentration quicker apart from loading dose. That is by using first infusion rate and then slows down. So we have Here we have a very first infusion rate, that is the Q1, and then after that it reaches the steady state plasma concentration, and soon we can move to a slower infusion rate. So it is a little bit of advanced how to calculate this two infusion rate, and we will not discuss this here, but you can try and read about it. Thanks for your patience hearing. These are my friends. Please like and share and subscribe my channel if you like this presentation. Thank you.